show by the principle of mathematical induction that for all n belonging to the set of natural numbers n, we need to show that 11 raised to the power of n plus 2 plus 12 raised to the power of 2n plus 1 is divisible by 133. Let us begin. Now here, before beginning, we need to understand the problem. Here we are not being asked to prove that this expression is divisible by 133. Rather, we need to show that it is a true statement by using the principle of mathematical induction, that it's true for all values of n belonging to the set of natural numbers, meaning any natural number n that we pick up, this statement always must be true. So that's what we have to show here. For this, what we'll need? We'll need to specify a statement here. So we'll consider Pn be the statement given by P of n such that we have 11 raised to the power of n plus 2 added to 12 raised to the power of 2n plus 1 is divisible by 133. So this is a mathematical statement. We're going to label this as number 1. We will need to verify that P of n is a true statement. Now how shall we do that? First, we will check if it is true for the first natural number 1. So that means for n equals to 1, P of 1 this is going to become 11 raised to the power of, we'll replace n with 1 plus 2, that's going to be 3, added to 12 raised to the power of 2n plus 1, so that's going to be cubed. Now 11 cubed plus 12 cubed, that's going to give us 3059. This number is indeed divisible by, this is divisible by 133. We can verify that because 133 times 23, that is going to give us 3059. Fine. So we can say here that the statement P of 1 is true. Well, we have shown here that the statement, original statement P of n, it's true for n equals to 1. Now, what we'll do, we'll have to also verify for other natural numbers as well. So what we'll do, we'll consider here that P of m is true. So this is an assumption. We are assuming that P of m is true, where m belongs to the set of natural numbers. Fine. Now, if P of m is true, then we can rewrite the statement P of m as 11 raised to the power of m plus 2 added to 12 raised to the power of 2 times m plus 1 is divisible by, this is divisible by 133. So let's call it statement number 2. Fine. Now using this statement, we will show that if we consider the next natural number, that means we will show that to show the P of m plus 1, P of m plus 1 such that 11 raised to the power of m plus 1 added to 2 plus 12 raised to the power of 2 times m plus 1 added to 1. This statement is divisible by 133. This expression is divisible by 133. We need to show that this statement is true. Fine. So how do we show that this is a true statement? So using statement number 2, since it is already mentioned here that P of m is a true statement, meaning 11 raised to the power of m plus 2 added to 12 raised to the power of 2 times m plus 1 is divisible by 133. So we can express it as a multiple of 133. So let's call it 133 times lambda, where lambda is a natural number. Lambda belongs to the set of natural number. Fine. So let's call it number 3. So we're going to use number 3 to show that P of m plus 1 is true. So now we will consider 11 raised to the power of m plus 1 added to 2 plus 12 raised to the power of 2 times m plus 1 added to 1. Now what we'll do, we're going to rewrite each of the two terms. Now the first term can be also expressed as 11 times 11 raised to the power of m plus 2. So here we have used the law of exponents, and then the next term is going to become 12 raised to the power of 2 times m plus 3. Let's keep it as 2 times m plus 3. Now, in the first term, we have 11 raised to the power of m plus 2. We can take the help of equation number 3. So here, we will keep 11 raised to the power of m plus 2 on the left-hand side and transpose the second term to the right-hand side. So that will be 11 raised to the power of m plus 2. So here, we can replace it with 133 lambda minus 12 raised to the power of 2 times m plus 1. Added to 12 raised to the power of 2 times m plus 3. Fine. Now, let's multiply 11 with each of the two terms. So we have 11 multiplied to 133 times lambda minus 11 times 12 raised to the power of 2m plus 1 added to 12 times 12 raised to the power of 2m plus 3. Right. We'll keep the first term as it is, 11 times 133 times lambda. Now from the second term and the third term, if we pull out 12 raised to the power of 2m plus 1 as the common factor, here in this place, in this second term, we'll be left with 11. Then minus, so from 12 raised to the power of 2m plus 3, if we pull out 12 raised to the power of 2m plus 1, we'll be left with 12 squared. Fine. So this is going to be equals to, now we have 11 times 133 lambda minus 12 raised to the power of 2m plus 1. Now 11 minus 12 squared. 12 squared is 144. So 11 minus 12 squared, that's going to be negative 133. So which means that we now have 11 times 133 lambda added to 133 times 12 raised to the power of 2m plus 1. Okay. Now, from both of the two terms, we are going to take 133 as the common factor. So that gets multiplied to 11 lambda added to 12 raised to the power of 2m plus 1. Fine. Now, from both of the two terms, we're going to take 133 as the common factor. So that means we have 11 lambda added to 12 raised to the power of 2 times m plus 1. Now, we have already considered m and lambda to be some natural number, which means the entire expression can be replaced with beta. That is, in essence, where we have considered 11 times lambda added to 12 raised to the power of 2m plus 1 to be equals to beta, and beta belongs to the set of natural numbers. In other words, what we have done here is we have shown that this expression equals to 133 times beta. So here we have shown that the expression 11 raised to the power of m plus 1 added to 2 plus 12 raised to the power of 2 times m plus 1, this expression is divisible by, this entire expression is divisible by 133. In other words, what we have verified here is that the statement p of m plus 1 is a true statement. So this is true. If this is true, then we can generalize it and we can say that hence the statement p of n is also true. P of n is also true, and it's going to be true for any natural number that we pick up. So that means it's going to be true for all natural number belonging to the set of natural numbers n. So by using the principle of mathematical induction, we have successfully showed that the statement p of n such that we have this expression, this is going to be divisible by 133 for all natural numbers n belonging to the set of natural numbers n.